lekciju. Lekcija ir angliski, tādēļ es pārēšu uz angļu valodu. Again, dear colleagues, dear students and guests, it is my great pleasure to welcome you to this guest talk, which will be presented by Professor Trifonova. And without his talk will be on the origin of genes and genomes. But before we proceed with the talk, a little bit of introduction about who Professor Trifonova is will be presented by Professor Jakobsen.
Paldies. Now I'm friends with Professor Trifonova for a quarter of a century. We met in Israel. Trifonova started his career as a physicist, and gradually he moved into physical chemistry and then to system analysis, sequence analysis. And he is a world renowned and pioneer many things in sequence analysis before the informatics was taken over and used as a term. His major contribution when he arrived from Moscow was to calculating that DNA in nucleosomes is not king like proposed by French Strict, but could be smoothly bended. And it is because of intrinsic property of denucleotides along DNA. It was a major contribution. He became professor at the Weizmann Institute. Then he moved into sequence analysis, even DNA as a language, and a lot of physical chemistry, sequence physical chemistry, base DNA and curved DNA, and everywhere he was pioneering, opening new vistas. Recently, he went, actually a few years ago, 7 years ago, started to think about origin of life in nucleotides and sequence analysis regarding to that. And now he has a well-rounded theory with more than 100 definitions of what is life, and everything is based on the evolution of nucleotide sequencing in DNA. Yesterday he gave a very exciting lecture about proteins, structure of proteins, modular, and it was also well received, and people noticed fresh output on this unexpected problem. So with further ado, Edward, the floor is yours.
Thank you very much for the generous introduction. I feel warm. May I ask women to give me permission to take over China? I would say that in the American audience, that suggestion would sound very strange. So this is my first ever talk in Latvia, and I dedicate that talk to my father, Machulan Grigoriy Yurovich, who was executed by fellow Bolsheviks in Stalin terror times. And my talk would be about origin of genes and genomes, and many people, especially younger people, smile when they see that some old scientist or some stops the origin of blood. She said, when you become interested in the beginnings of life, that means that you're approaching the end. The reason why I got interested in the subject is not ambitions of the old man, but rather realization that I just know sufficiently large amount of respective knowledge so that I may try to make sense of what people thought about how life started. I start with the genome to say that in our beginning of genome era, we consider the genome as something holy, because all our life, all our functions, malfunctions, they're all written in the genome, and since probably it will take another 50 years before we'll realize what every letter of the 3 billion letter genome is responsible for, it will stay holy, and the place for the soul, although I'm not a religious person, I don't think that there is a place for soul there. However, even religious people could well study the genome, the genes, from the point of view of their origin, without compromising their beliefs, because my best friends in Israel who are deeply religious and who are working on the molecular biology in general and the origin of life in particular, they simply say that there is no contradiction. They study the deeds of God. So do I, and say, if indeed it was all created by God, then I would like to know how exactly he did it. So the holy genome, as it turns out, is not as complex as we used to think. First of all, the protein coding genes and RNA coding genes take only about 3% of the whole genome. All the rest is so-called non-coding DNA. But this is misnomer. There is no non-coding DNA. Even the most primitive DNA sequences which you find there, like down there repeats, simple sequences, they do have a function. So, of the non-coding DNA, 97%, about 45% are transposable elements, and about 3% of simple sequence repeats. But if you look to the rest of the genome, you realize that those simple sequences are frequently interrupted by point mutations, so that they're not strictly random repeating sequences. They're called cryptic simple repeats. So in the first assembly of human genome by Lander and group in 2001, they wrote that repeat sequences, both simple repeats and transposable elements, account for at least 50% of the genome and probably much more. And I'm going to talk about that and to uncover that even protein coding sequences are actually dominated by simple repeats, and there I call it domestication products. That is, it starts with simple repeats, then they mutate until they come to certain functionality and improve it by further mutations. Most of you probably heard about triplet expansion diseases. These are called by what I call aggressive triplets, you see that it repeats GCU, 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 but if you read it not as GCU, as CU, GCU, GCU, G, you have a second repeat, second triplet repeating, and also you could read it as UGC repeating, and when you take complementary strand, you similarly get triplets AGC and GCA and CAG repeating, all in the same DNA duplex. So these 6 triplets are all belong to the same duplex and represent the aggressive family of GCU. What to the things which I'm going to describe here, accidentally, my student, Zohar Koren, he got interested whether the first exons are any younger than second and third exons. He looked at the amino acid composition of the first exons and was surprised to find that they are reaching simple repeats, amino acid repeats. It turned out that those repeats which are found in first exons, and as a matter of fact in any protein coding sequences, as we found out later, those repeating amino acids are all encoded by aggressive repeats. Like leucine could be CTG, or the same as GCT repeating, or CTT, the same as GAA, if you take a complementary. Alanine is encoded by all aggressive repeats. And so forth. The only exception from that rule is phenylalanine and cysteine, which are at the bottom of the list here, and they really don't make too many repeats. So here we have occurrence of 3 peptides. Then the same codon repeating 3 times. Naturally, if it repeats 15 times, then this 3 appears there, if I'm not mistaken, 12 times. And the most frequent is leucine, next frequent is alanine, and so forth. So that they all together make 92% of all repeats. Actually, all amino acids could repeat, but many of them are just marginally so repeating. If you take eukaryotic proteins in general from a rather large collection of hosts and all, you get about the same picture. The same aggressive amino acids are on the top of the list, making together 75% of all repeats which are found there. But in prokaryotes, where repeats are generally pretty rare, you get the same result. 89% of all the repeats which you find there, amino acid repeats, are of the aggressive families. So we're coming to a very simple idea. Maybe those expansions which cause neurodegenerative diseases and chromosome fragilities, maybe this is actually a norm and not a disease. That is, they spontaneously emerge here and there within the protein coding sequences as well, and make the whole background of the sequences. So could it be that protein sequences actually are all originally made from the aggressive repetitions? And we don't see all the original repeats just because they have extensively mutated. If so, then there are 3 things which one would expect. First of all, the ideal repeats of some codons would be present, and indeed they are. Second, if you take 2 identical codons and look what is in between, so-called sandwiches. The codon flanked by two identical codons. If these two identical codons come originally from continuous repeat of these codons, then the middle one would be likely either the same codon or point mutation of it, more frequently than anything else. This is the second prediction. And the third prediction, if this is all true and the coding sequences are found by the expanding triplets, then after mutations, even when you already don't see repeats, you still have domination of these aggressive triplets. Those codons which are more often done in repeats should be also of higher usage in non-repetitive sequences. We thus undertook analysis of the largest available non-redundant database of messenger RNAs of total 5 billion codons, nukes, rocks, viruses, organelles, altogether. To check these 3 points. Point number 1. Yes, indeed, all 61 triplets are found in repeating form more or less frequently. The dominating group is aggressive triplets. GCC group on the top, then GCA group, and then GA group. Tandem repeats of all 61 different codons are observed, the strongest for aggressive groups, as expected. So number 1 is all right. Now number 2, sandwiches. Here as an example, the sandwiches GCU, ABC, GCU are shown. Total 3 million sandwiches. And frequency of the middle triplets shown on the column to the left. You see that the most frequent sandwich triplet is GCU itself, reflecting the repetition of the aggressive triplets. But the next most common is GGU, which is point mutation of GCU, GAU, which is point mutation, then also CGU, GCA, and GCC, all point mutations, so they're all on the top of the list. What you would expect on the top of the list, if not the point mutations? You would expect the most frequent codons of the coding sequences. Exclude repeats and look what are the most frequent codons. Then you would expect that these most frequent codons would appear. The most frequent actually is GAA. And the next most frequent is AAA, but they are not on the top of the list. The top of the list is dominated by point mutations of the GCU repeating triplets. And that very picture is observed in majority of all other triplets, in all aggressive triplets, and in many other triplets as well. And third, the middle codons in sandwiches are most often first derivative of the flanking repeats. Now if you take sandwiches like in the advertisement of McDonald's, thick sandwiches with many triplets in between, then what do you expect? First of all, again, the most frequent is triplets itself. That is, even if, when you take as long as 100 distance between aggressive triplets, you still find the aggressive more often somewhere in the middle. So if you take the XYZ as formally repeating triplets, then you would expect XYZ more often triplet in the middle, and this is reflected by the curve on the left. It is always above the level 1.04, which is random level. So, in other words, when you don't see a repeat, but see only the triplets of that repeat, reflecting the origin of a whole sequence. It simply says, all right, you have many of X, Y, Z simply because this all started with repeating X, Y, Z. Same thing with the first derivatives. If you take all the first derivatives of X, Y, Z and look how they are distributed in the thick sandwiches, you find that they dominate there. And the shorter is the distance, the better the memory of repetition is kept, which is reflected by higher values for shorter sentences. So we conclude that the first derivatives between the identical codons in messenger RNA keep memory of initial tandem repetition of these codons. So now we could imagine how that all happened. It started with repeating, say, GAA sequence and on the top. And then slowly it started to collect mutations. The first, of course, mutations in one of the three positions, and then goes in two or three, and sometimes in all three, so that eventually you come to a sequence which already has nothing to do, nothing similar with original repetition. That is why we don't see those repeats right away. You see them only after some analysis, because many sequences already forgot where from they started. So now if you take proteins, better to say messenger RNAs, and ask what would be percentage of the most frequent repeat triplet in that protein. Then we get the black curve indicating that some of the triplets in natural proteins could occupy as 15 to 20% of total composition of triplets. While if you shuffle the sequences, turning them into random, you see the red curve where you barely get 10% of the most frequent triplet. In other words, again, as you would expect, if they all started with one repeating triplet, then after all the mutations, that one repeating triplet still would be dominating as much as 15–20%. So here's an example of a pretty ancient protein. We picked that example randomly. That is, we simply looked at the collection of those proteins which have more than 15% of this or another triplet, picked up from the top of the list, and it turned out that this was an ancient protein. So even in the ancient protein, you still see remnants of simple repeats. And if you take the regions, like look at the bottom right, we call them bricks. Look at this brick. It contains GAA 4 times and AAA point mutation of GAA, almost completely made of the triplet GAA or its first mutations. The other red bricks are about the same type, that is, they contain the GAA or point mutations of GAA, and you clearly see that the region which is colored green practically doesn't contain those GAAs, but contain another frequent triplet in this protein, in this messenger RNA, namely GCT and point mutations of this GCT. So approximately you could say that that messenger RNA originally was made, say, of 3 big pieces. One repetition of GAA, another one repetition of GCT, and the third one, again, repetition of GAA. Today, we don't see them as complete repetition, because after all, repeating sequence per se doesn't carry much of the message. And if you want the message to be informative, you have to introduce some measure of complexity into the message. But notice, when you reach some functionality in the process of repetitions, then you most likely stay close to that sequence, because it's not complexity for which nature is striving. It is function. So it can optimize that function. As a result, it would optimize it around high frequency of original repeating triplets. And now the third point. Let's take codon usage. And to make it clear, we deleted all the repeating codons. We now deal with messenger RNA sections which do not contain any repeats. And look what is codon usage. And we compared that codon usage with frequency of tandem repeats of these codons. So it turns out that the triplets in tandems which repeat more frequently, they also show high codon usage. This is a very fundamental result, irrespective of the hypothesis, irrespective of the theory. It simply says that those triplets which like to be repeated, they are of high codon usage in the codon usage table. And this appears to be a major factor which makes the codon usage. Here the codons are separated in 21 group repertoires, like Lucid has two repertoires. In the middle, right, you see Lucid UUA and UUG, and another Lucid you see in the middle left, CUX. And everywhere when you see in the left column, it is the frequency of the codons in non-repeating sequences. The most frequent codon also is of highest repetitive power. Each time, actually in 17 of 21 codon repertoires, the most frequent codon is also the most repetitive. This result, of course, came as a surprise, considering zillions of factors known to influence the codon usage. The literature on codon usage is gigantic. So is the number of factors influencing the codon usage studied. But none of them is as conclusive as the factor of repetitiveness of the codons. So more frequent codons keep memory tandem repetition of these codons in the distant past. The triplet expansion of codons is a major single factor shaping the codon usage. Now we're coming to an earlier work, which started in 1997, and which was answering the question, which were the very first messengers? To answer that question, we first analyzed which were the very first amino acids. And that is a tricky problem, because people only could speculate what were first, which were first. However, no matter how smart is speculation, it always carries some grain of truth. So in a way, they should correlate. The different criteria for amino acid chronology in evolution should correlate. And we discovered that yes, they do, and one could even make a consensus. So consensus order of appearance of amino acids in evolution is shown on the top. The first were lysine and alanine, and then aspartic, valine, cyclic, proline, and so forth. That evolutionary table of the triplet code turned out to be a very fruitful basis for theory of early molecular evolution. And one of the conclusions of this theory is that these codons appear in the order of highest term term stability, corresponding codon anti-codon pairs, which is very logical, because stability plays a key role in the stability of the molecular association in life and in early life as well. So essentially you have this diagonal dependence of the thermostability and appearance of amino acids in the pairs, the complementary pairs of triplets shown here, they essentially follow thermostability so that GC and GCC, which are complementary. GGC is the most stable of all possible complementary pairs. And at the bottom you see DNA and LAA least stable. So they follow this simple dependence of stability and appearance in the evolution. So the table says, therefore, that the very first messenger was simply repeat GGC, 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 get complementary GCC, 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 GCC. One strand called license, GGC, and another strand, GCC, repeat, then called alanine. Then we started to mutate. So the GGC mutated to GAC, and you got codon for aspartic, which is just next amino acid to come in the order of their appearance. Or GCC would mutate to GUC, and you get radian, which is again next in the row. When glycine GGC triplet to mutate into GGG, then its complementary would be CCC, which is proline, which is again next in the row. Serial proline, of course. So you have two stages in the development of this table. First, you have homotriplet stage, which is replication of GGC, 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 and complementary GCC, GCC. But the next stage is variations. You get other triplets form, and you have two stages: just self-replication, and then self-replication with variations. That brings to a definition of life, which is very much in accord with definition of natural selection given by Darwin. So essentially, the Darwin's idea was that if you have a variation which is useful, then respective progeny inhibits that variation and it will spread. So rephrase the Darwin's definition, one would say that individuals with useful variations will self-reproduce. In other words, life, which is based on natural selection, so life is self-reproduction with variations. And that's exactly the definition which comes from the theory of early molecular evolution and from the evolutionary table of codons. That is, it starts with GGC, GGC, and complementary GCC, which is just replication. And then, with introduction of variations, you get also self-reproduction with variations. And the border between life and non-life is the border between the first line of the table of codons and the rest. So we're coming therefore to that definition. Life is self-reproduction with variations. I have to say that after publishing this definition, I did not get any interesting response, no even citation. Although, as I was told by many people working in origin of life, any values that was in Darwin. It happened that later on, I came to the idea to generate the consensus definition using known definitions. There are about 150 definitions. They all contradict each other, but they all have their elements of truth. So I counted those words which are used by those 100 some definitions, and grouped them by the meaning, because they system is a system, is organization, is organism, is order, network. This is all description of the same thing, system. So I got 10 groups. One, of course, is life itself, and then 9 groups of definition. Sorry, I don't know Latin. And then when you look to this, well, of course, you could make a long definition, which would include all these categories. And some of the classics of philosophy of origin of life would agree with that definition, all right? But if you do a little bit of thinking, just trying to minimize, to reduce it to something which, as mathematics demands, would be both sufficient and necessary, then it turns out that sufficient and necessary candidates of this list are reproduction and evolution, or self-reproduction and variation. Because if you do have reproduction of something, then surely you have some system where it happens, some material from which it's all built, some degree of complexity of the system. These are all not a basic elements, but derivative. The basic elements, in my opinion, in definition of life, which probably make it both sufficient and necessary, are self-reproduction and variation, evolution and reproduction. So we come to the same definition as we got from the code evolution theory. So definition of life is described by definientia, systematic chemicals of force, of which reproduction and evolution appear to be both necessary and sufficient for the definition of life. So life is self-reproduction, is variation. As the best example of other definitions given in literature, I give the definition of body. Any system capable of replication and mutation is life. And I'm very proud by the fact that both giants of early evolution and evolution, Darwin and Parry, give essentially my definition. So, life started with just a simple recognition of aggressive different and consecutive expansion of the triplet, and subsequent mutation within those repeating triplets. Life continued then to spontaneously emerge with the primitive early genomes, and further on, in form of replication and expansion and subsequent mutations of other tandem repeats as well. Life never stopped to emerge. I was asked by the scientist to write an opinion paper on the subject, and I wrote that paper with the title, "What is Life?" And I was bombarded, just for fun, looked at that in Google. I was bombarded by reaction. And one reaction was, "This is a very bad paper, but extremely interesting. I couldn't get it better."